We still in the procedure for sketching the root locus. As I mentioned earlier, we have 9 rules. We have completed rule 1 until rule 7. Today we will continue with rule number 8, which is angle of departure and also angle of arrival. Rule number 8 applicable if we have open loop, we have complex open loop pole and zeros, or zeros, and or zeros. Okay, that means if we have open loop pole, or if we have open loop zero, or we have both, then we have angle of departure and angle of arrival. That means not all root locus we can use rule number 8. It is applicable only under these cases. Okay, angle of departure is related to pole. When we have pole, we have angle of departure. Why? Because we know that the root locus start from pole. So when we start from pole, we call departure. It start to move on, to go out. An angle of arrival is related to 0. Why? Because 0, all root locus finally end at 0. So we call arrival. So again, you should know departure for pole, arrival for 0. And it is only applicable when we have complex pole or 0. These are the formula to calculate the angle of arrival. Theta A here, I refer to arrival. Angle of arrival, A. And D is departure, angle of departure. I will elaborate the formula in the next slide on how to calculate angle of departure and also arrival. Let's take this as an example. Let's see A. Let's say we want to find angle of departure. Okay, departure at A. A here, this is A. A is a point, we have pole. Again, this is a complex pole, that's why we have angle of departure. Angle of departure here is theta 1. Theta 1 here is the angle of departure. Okay, that means the angle, it start to move, to go out. Okay, we have one 0 here, 1 0, another 0 here, pole 1 2, 3 poles. Okay, we will calculate angle of departure and also arrival based on the calculate using the root locus properties, which say that total angles of 0 minus total angle of poles equal to plus minus 180 degrees. So we use this formula. Total angle of zeros minus pole equal to 180 degrees. It can be plus, can be minus. Same point, same direction. So from here, for this figure A, we can say that theta 2 is the angle for the 0. Remember, angle always calculate from 0 degree. 0 degree is positive x. This is 0 degree. Always calculate from here, the x. So theta 2, I better. Theta 1 is for pole, so minus theta 1 because always minus angle of pole. Theta 2 is for the 0, theta 2. Theta 3 also 0 plus theta 3. Theta 4 is for the pole minus theta 4. Theta 5 for another pole, theta 5 equal to 180 degrees. I use positive. That means if I want theta 1 is the departure angle. I bring theta 1 to the right. That means theta 2 plus theta 3 minus theta 4 minus theta 5 minus 180 degrees. This is the formula to calculate the angle of departure for this particular example. Let's see here, another one, B. B here is to calculate angle of arrival. Because B now, for this case, the point B here is a 0. That means angle of arrival theta 2. Using the same properties, we can get the same formula. That means minus theta 2, minus theta 1. Theta 1 always minus because it is from pole, plus theta 2 plus theta 3 minus theta 4 minus theta 5 equal to 180 degrees. So we can get theta 2 is theta 1 plus theta 4 plus theta 5 minus theta 3 plus 180 degrees. Theta 2 is the arrival angle. That means we use the properties, which is all 0 angle is positive, all angle for pole is negative, then we 0 minus pole must be 180 degrees. Let's move on. We will do one example on how to calculate the angle of departure. Any question before we proceed? Find the angle of departure from the complex poles and sketch the root locus. Okay, now I want you to first, we want to sketch the root locus. Now use rule number 1 until rule number 7 and sketch the root locus. Please do it now. This will help you to understand root locus and familiarize yourself in sketching root locus. Try rule number 1. Apply rule number 1 until 8, until 7. Then we will do number 8. Right, so we have minus 3 whole minus 1, here minus 1, J1. J1 here,
Negative
minus
J1.
J1. So we have here and here. Here is minus 1. And we have 1 pole, 1 0 on at minus 2. Now apply rule number 3. You have to go rule one by one. Rule number 1, number 2, number 3, number 4, and so on. Rule number 2 say they are symmetry. So all root locus are symmetry. Rule number 3. Now apply rule number 3. What rule number 3 say?
Real axis segment.
Real axis segment. Okay. So now find root locus on the real axis. Where are the root locus? How to determine the root locus on the real axis? What is the step? There are 1 pole, 1 0 on the real axis. So how can we determine which area, which region that we will have root locus?
So after the minus 1,
Again?
after the odd number, the minus 1, the left values.
Left of the odd number. Left to the odd number. This is number 1, number 2. Left of odd number. So root locus must be here. Left of odd number. So no root locus here, no here. Any question before we proceed?
Doctor, how about 0 to negative 1?
0 to negative 1.
Or
0.
because it's not
We are discussing
real
rule number 3 applicable to
real
real
axis, right?
axis only.
Okay, okay.
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 Pole here are complex pole. So we will not count complex pole for
Okay,
rule
right.
number 3.
Understand.
Okay, rule number 4. What rule number 4 say? All see your note. Rule number 4.
Starting and ending point.
Starting and ending point. So now I want you to put the arrow for the root locus. All root locus must have arrow showing the direction. So now put an arrow. Currently, we only have root locus between -2 and -3. Okay, now put the arrow. Where are the arrow? Anyone can help? How can we put arrow?
From poles to 0.
So rule number 4 say all root locus must start from poles and at 0. So arrow must be like this.
To the right. Yes.
Always from pole to 0. So in root locus, you should not write the number 1, 2, 3 in the root locus. That is just a guideline. So that's why I remove the number. And rule number 4 also say that root locus start when K0. Remember, root locus showing closed loop pole when K move, when K change from 0 to infinity. So K infinity here. So all must be shown on the root locus. Let's move to rule number 5. What rule number 5 say? Anyone? Rule number 5?
Behavior at infinity.
Again, louder.
Behavior at infinity.
Behavior at infinity. Okay, my first question. How many finite pole we have?
3.
How many?
3.
3. Yes, 3 finite pole. Finite means we can see, we can obtain. How many finite zero?
1.
1, Doctor.
1 finite zero. How many infinite zero?
1.
How many infinite zero?
2.
1 or 2? Rule number 5, the question that I asked is also related to rule number 4. Rule number 4 say all root locus must start from pole and at 0. Right? That is rule number 4. So we have 3 poles. We have 1 finite 0. There must be another 2 0. So that our root locus complete. All pole must end at 0. So how many infinite 0?
Two. Two.
Therefore, there are 2 infinite 0. So that total here is 3. So all pole can go to all 0. That's why we separate into finite and infinite 0. The infinite means 0 at infinity. Okay. We also have infinite pole, but in many cases, pole are more than 0. That's why usually in many cases there is no infinite pole, only infinite 0. Any question here? Then rule number 5, continue to answer where are the infinite 0. We say there are 2. Where are they? Because pole, the root locus, from pole 1 to go to the 0. So where are the 0? That is also covered in rule number 5. What's the other information in rule 5? Anyone can help. Now we want to find where are the infinite 0. Yes.
To find the number of asymptote.
Okay. Then
Number 2 is we find the real axis intercept.
realize the intercept. The other
And
one,
we find the angle.
angle. Okay. So rule number 5 also related to finding asymptote. What is the significance of asymptote? Asymptote will help us to locate the infinite 0. Asymptote is a straight line used to help us to locate the infinite 0. That's why asymptote the formula of asymptote is number of pole minus number of 0. So how many asymptote we have? How
2.
many asymptote? Yes?
2, doctor.
2. 3 minus 1.
3 minus 1. Yes.
2. Okay. Because, remember, we also have two infinite zeros. That's why we have 2 asymptote. Because asymptote will help us. Later you find that if you have 4 infinite zeros, you have 4 asymptote. Because again, pole minus 0. Finite pole minus finite 0. We know asymptote there are 2. Next, we need to calculate for the what we call in real real axis intercept. Real axis intercept. Sigma. Please check your note. The formula is, what is the formula?
Total of pole
Pole, total, I put this, total pole,
minus total of zeros
total zeros, divide
divided
by
by number of asymptote.
number of asymptote. Or usually we write this one, the same.
Oh.
Okay.
Minus 0. Okay.
The sign is different. Okay. The top one is total pole, total value of poles. The bottom one is number of poles. So sigma here, sigma equal to, here I make what I mean, total of pole mean we add all pole. All pole I have minus 3 plus, this is another pole, minus 1 plus J1 plus minus 1 minus J1. All pole we add on the real axis and also on the complex poles. All minus 0, 0 at minus 2. Divide by 2. 2 is P minus Z, 3 minus 1. So here we get minus 3. So we can see that the one with the J will be cancelled out, plus minus. So minus 3, minus 1, minus 1, so minus 5, plus 2, minus 3 over 2, 1.5. $1.5 is here. 1.5 negative. Then the next formula to be used is theta. The angle of asymptote. Theta asymptote, remember what is the formula? Someone, can you read the formula?
2k
2k
plus 1
plus 1
multiply with
pi
pi over number of
e
pole
minus pi.
minus number of zeros.
Okay. And k from 0 to 0, 1, 2, 3, and so on. We apply this formula, we get I want to put this is 2. Okay. So when k0, we get pi over 2, 90 degrees. When k equal to 1, that means 3 over 2 pi, 270 degrees. If you put -1 mean -1, -2 will be -90 degrees, and so on. You will see it's actually you go around and get at the same point. Usually number of asymptote there are 2, we only need 2. -90 degrees is equal to 270 degrees. Any question before we proceed?
No, Doctor.
So now is to show the asymptote on the S-plane. This is the real x-intercept. We have 2 asymptote, and the angle will help us 90 degrees. So 90 degrees mean this one. This is asymptote number 1. We have 2 asymptote. Another asymptote 270 degrees. This is another asymptote. Asymptote. This is how to show asymptote on the root locus. Next, rule number 6. What rule number 6 say? I will erase all this. What rule number 6 mention?
Real axis, break away, and break in points.
Break in
Break
and
in
break
and
away.
in point and break away point.
Break in point and break away point. Sorry, I somehow erased this. Break away and break in point. Do we have break away and break in point? What my question? Do we have break away and break in point? Yes, no.
No.
No, doctor. This is
No,
No,
why
doctor.
no?
it's a closed loop.
Huh?
It's a closed loop. We only have breakaway and break-in points in open loops.
The answer is no, but the reason is not correct. Anyone else? Why no break in, no break away point?
Because there is no poles and poles side by side.
Yes. Break away happen only if we have pole like this. side by side, together, adjacent. Because previous rule say that all root locus must be from pole. So two arrows going out from poles, then you can imagine that they collide. That's why they break away, something like this. So this point we call break away. So it happen only if we have two poles side by side. How about break in? Break in happen if we have pole, if we have zero
Zeros with zeros.
with zeros. Okay, zeros with zeros. We also have root locus here. Is because we know it always end at zero. So always arrow going into zero. But it come from somewhere else, from poles. Maybe pole here. Maybe this is just an example. It go here. It go here. They must be symmetry. This is not symmetry. So all must be like this, and this is called break-in point. In the example that we are doing now, there is no such case. No case like this. That means no break-in, no break-away point. So you should understand that not all rules are applicable. Although we have 9 rules, only rule number 1, rule number 2 applicable to all. Rule number 3, if we have pole and zero on the real axis. Rule number 4 applicable to all, because always start from pole to zero. Rule number 5, only if we have asymptote. Rule number 6, if we have break away and break in point. Let's move to rule number 7. What rule number 7 said?
Find the J omega crossing.
J omega crossing. So rule number 7 deal with J omega crossing. J omega crossing means this exists, J omega exists. Imaginary exists. In your opinion, is the root locus in this example cross J omega?
No.
No. No or yes? Okay, let look into this in detail. What is the importance of asymptote? We discussed before. What is the importance of asymptote? Asymptote will help us to locate the infinite zero, right? So zero here, infinite zero, maybe here. At infinity, actually, no zero. Okay, but it's at infinity. So the asymptote we say that the root locker must start from the pole. So pole here we'll use this asymptote to locate 0. Here also, always we'll go try to locate the 0 by following the asymptote. Any question for this at this at this stage? Any question? Do you understand the importance of asymptote?
Doctor, so in this question, there are no imaginary crossing, right?
Yes.
Okay,
This,
understand.
for this example, the root locus is not crossing the j omega axis because always follow asymptote will go up. Okay, and we ideally it will meet the asymptote at one point, but it will never cross the j omega axis, right? Never cross j omega axis. That means no. That means rule 8 or 7. Rule 7. Rule 7 is not applicable to this system. Rule 7 is not applicable. It is applicable only if you see that the root locus cross j omega axis. One question. When okay, before that, always we must put k start from k0 and end at k infinity. Root locus, again, I want to say the root locus showing the closed loop pole. Root locus show the closed loop poles when k, the gain, k changes from 0 to infinity. This k, remember this k. When this k change from 0 to infinity, this is how the root locus look like. This is where the pole. At one time, there must be 3 poles. 3 closed loop poles. Always. Okay. So at K0, these are the poles. Here, here, and here. When K1, it increase. Maybe here, maybe here. Sorry, it start from here. Maybe here, maybe here. K2, it increase. So then maybe 2 poles, 3 poles. Here, here, and here. So it show closed loop poles. My next question, at what K, the system become unstable? Anyone can answer. At what value of K, the system become unstable? How can we know what is the indicator that the system is unstable? How can we know, how can we check system stability?
So we apply the RH criterion to check whether the system is stable or not.
That is one thing, one approach. As we already have the root locus, we can directly obtain that one also. So how can we determine system stability beside Rosowitz criteria? How we define system is stable or unstable? In what condition the system become unstable? When system become unstable.
System become unstable at the right half plane.
System become unstable if we have closed loop pole at the right half plane. If we have a pole here, this is right half plane on the right of J omega axis. So based on this root locus, will the closed loop pole be in the right half plane? Remember, although we just we put line, this is actually many points of closed loop poles. Okay, when K change, many pole here. Finally, we plot by having a line, but it's actually based on many points of closed loop poles. So we can see here the closed loop pole will never cross J omega axis. Always on the right. Oh, sorry, always on the left. Will not go to the right. That means the system is always stable. All value of K, if we use, system will be stable. Always stable. Will not go to unstable. So that means no K here. The answer is the system will always stable. at all value of k. Later, we will see another example that we can find k when the system become unstable. Any question?
No, doctor.
Once we have rule number 1 until 7, that now we look into rule number 8, the one that we discussed earlier. Rule number 8 related to departure and arrival angle. My question, do we have departure angle here in this example? Yes or no? See your
Yes.
see your notes, see your slide. The whether departure and arrival angle exists or not?
No, doctor.
Yes. Do we have a departure angle? Yes or no?
Yes.
Yes. Why?
Because we have complex force.
Because we have complex pole. You are right. Yes. Because we have in this case 2 complex poles. We have complex poles. Remember, complex poles or zero, then they will come in pair, plus minus. So always at least 2. Next question. Do we have arrival angle?
Yes, doctor.
Yes or no?
Okay. Arrival angle.
Arrival angle.
Arrival angle. No.
No? Yes or no?
No, because we don't have the complex zero.
So the answer is no. Because no complex 0. Okay? If we have both, then we will have both angles. If we have one, if we have only complex pole, then we only have departure angle. If only a complex 0, then only arrival angle. If we do not have complex pole or complex 0, then rule number 8 will not be applicable. Again, you must determine which rule to be used. Now let's use the formula to calculate the departure angle. The departure angle always, the departure angle is this one. Let's say we focus on the pole at at positive j. So this is what we meant by departure angle. This angle, theta. I put theta 1. Departure angle is actually to help us to start the root locus. Of course, this is just a sketching, not an exact one. It's just to help us to show, to help us, to guide us to start the root locus. Okay, so we need to get all the other angles. This is theta 2. This is theta 3. And another one here, theta 4. Or we need to find all angle, 0 or poles, 0 and poles, to the point that we want to calculate. Then we use the properties we say that minus theta 1, because theta 1 is pole always negative, plus theta 2, 0, positive, minus theta 3, minus theta 4, equal to 180 degrees. What we want to calculate is theta 1, then I can move theta 1 to the right. That means theta 2 minus theta 3 minus theta 4 minus 180 degrees. Now, I want you to find theta 2, 3, and 4. Now find theta 2, theta 3, and theta 4 based on the triangle using trigonometry. We know the coordinate, we know the length, and so on. Then we can calculate theta, the angle. Now find all the thetas, all the angles.
Doctor,
Theta 2 here,
oh,
theta 2,
excuse me, doctor.
yeah.
Doctor, when finding theta 4, can we directly write just 90 or do we have to show the calculation proving it is 90?
No, you can directly.
Okay, doctor.
Theta 2, we know is 45, right? So 1, tangent 1, 45 degrees. Theta 4, always 90 degrees. Theta 3 is like this, theta 3, 1 and 2. Theta 3 is inverse tangent, 1/2. Calculate, you get 26.6 degrees. Then theta 1 is theta 2 45 degrees minus 26.6 minus 90 degrees minus 180 degrees. Finally, you will get minus
251.6.
1.6. Minus, that means if you convert to positive, we get 108.4 degrees. That means theta here is 108.4 degrees. This is known as the departure angle. You can also calculate for the second one, because we have two poles, two complex poles here, but they are always symmetry. So here will be also 108.4 degrees. We normally calculate only once. The other one also the same, but in different direction, negative direction. Any question?
Doctor, how to calculate theta 3?
Theta 3. Theta 3 is this. This is theta 3. We know the angle, we know the pole here -3. This is the triangle, right?
Okay, okay. Nampak,
This is
nampak.
1, this here 2.
Okay, okay.
So we use this. Okay, we take a 5-minute break. We will continue with rule number 9, the last rule, but a very important rule. Rule number 9 discuss about plotting and calibrating the root locus and finding the gain. Okay. All point, we know that all point on the root locus satisfy two criteria. Magnitude and also angle. Okay, we know that the magnitude must be equal to 1, K GS HS equal to 1, the magnitude, and also the angle. Angle KGS HS equal to 180 degrees. Both all pole on the root, all point on the root locus, which are the poles, satisfy both criteria. So by using the criteria, the properties, especially the magnitude properties, we can find K at any point. We say that, let's say this is the root locus. I plotted from from MATLAB. Normally MATLAB does not give the arrow, so we should know the direction. Okay, we know that K start from 0, here K0, K0 here. So we know the pole when K0. But how about another point? Can we get, if I need point here, how can I get K? This point, K. K here can be obtained by using rule 7. K on the j omega axis. But how about another K, another point? K, all K is very important. So K determine the location of the closed loop poles. Rule number 9 discuss on how can we obtain the value of K. Remember, K is here in the block diagram. K, this K is important. So if we know K, then we can know the behavior of the system, whether the system is stable, whether the system is on the j omega axis, whether the system is under damped, over damped, and so on. All depend on the value of K. And K can be used for a simple design. We say gain adjustment. Gain adjustment refer to adjustment of K. Adjust the value of K to achieve certain desired specification. In design, in chapter 2, in which we will discuss control system design, PID controller design, we will start by designing a simple controller known as gain adjustment. Okay, this is the one that will be used, rule number 9 will be used in designing a simple controller known as gain adjustment. The gain at any point on the root locus can be obtained by using this formula, because we know that K GS HS equal to 1, the magnitude. So K is obtaining by using this formula. If we know S, let's say here, let's say I want K here. I know this value, and this I know the point here. Then this S can be substituted here into GSHS. Then we can solve for K. This value substitute here. Okay. Then we get here maybe S equal to we get S. That S value. Actually, minus zeta omega n plus j omega d. That one letter. Or it can also be represented by because this is g over g multiplied with h is actually pole 0 divided by pole numerator over denominator. Then we inverse 1 over, then it will be it also is actually is a symbol of pi. Pi meaning capital pi meaning we add. Oh, sorry, we multiply all. This is a symbol of the sigma is adding. This is in contrast is multiplication. Length, we can use length. Length of poles to the point. Divide by multiplication of all length of 0 to the point. How this one reflected here, I will show. Here is this. This means if I want K at this point, the one that I highlighted in red here, I want at K here, what I need to do is to find the length of pole to the point. Oh, these are pole here. There are, in the root local, there are 3 poles here. Okay, I need to find the length. The length L1. Okay, if we know the coordinate, then we can use Pythagoras theorem to calculate for the length. L2 here, length number 2, L3, length 3. And if we have 0, then we get also the length of 0. So here is actually L1 multiply with L2 multiply with L3 divide by, if we have pole, let's say we have pole here, then divide by pole. If not, divide by 1. Because no pole. No, sorry, no 0. If we have 0, this is example here. I need point here, then L1, L2, 3 and 4. Then K is L1, L2, L3, L1, L3, L4 divided by L2. So we have 2 formulas. One by substituting the value here, the other one by finding the length or the distance between the point to all pole and all 0, and use the formula. Pole divided by 0. Now let recap on overshoot, zeta, settling time, and peak time, and also all other time response specifications. Let's say I have an under-damped system. If I plot on the S-plane, we have two poles. Under-damped response means zeta between 0 and 1, and we have complex poles. And here is we know that for other damped response, we have two poles, which is at minus zeta omega n plus minus j omega d. Please refer to 3133 notes. These are important. Also minus zeta omega n plus minus j omega d is omega n 1 minus zeta squared. That means here is minus zeta omega n, and here j omega d, minus j omega d. If we know the location of the poles, and take the distance to the origin, you will see that the length here is omega n. The length is omega n. And theta here, if we can take the angle here, theta, zeta is cos theta. When we take cos, we get zeta. We get the damping ratio. If we know zeta, theta, the angle, then we can calculate zeta. And we know that zeta is very related to overshoot, in which overshoot equal to exponent zeta pi divided by 1 square root 1 minus zeta squared. So if we know the location of the pole, we know theta, we know zeta omega n, we know j omega d, we can calculate for zeta the damping ratio. Once we get damping ratio, we get overshoot. And we know that overshoot and damping ratio are inversely proportional. If we increase zeta, then overshoot will be decreasing. If zeta 1 means critically damped system, overshoot 0. If zeta 0 is an undamped, which last overshoot, it is actually oscillatory system. Please revise all this. And we also have formula. Settling time 4 over zeta omega n. You can see that it is very much related to the real axis, zeta omega n here, 4 over zeta omega n. And peak time, pi over omega d. Peak time related to here, omega d. Here, omega d. Okay. So on the real axis is related to settling time. On the imaginary axis, it is related to peak time. In control, we want to achieve, if applicable, if possible, we want to achieve all in good condition. We want a faster system. We want low settling time. We want low peak time. We want no overshoot. Those are a normal desired specification. Therefore, if we have a root locus, then we can use rule number 9. Let's say rule number 9 is for this system. We can find the value of K here, K, such that the system operate with 20% overshoot. We can find K to obtain 20% overshoot. How can we do that? If we know 20% overshoot, we can calculate for zeta, because we know overshoot is related to zeta. Zeta is 0.456. Zeta, please check your note, previous note also, 3133, on how to get overshoot to zeta. I mentioned just now that theta here, zeta is actually cos theta. If you, that means theta we can get by taking cos inverse 0.456. I'm not sure the value. 6. Sixty-two degrees, 62.87 degrees. From the root locus, we can draw, this is called zeta line. Okay. We can draw zeta line, which have 62.87 degrees. I can draw zeta from here, zeta line from here, 62.87 degrees. That means in root locus, in chapter 1, in chapter 2, you need to have a tool to measure the angle. Use that. What technique you can use to measure angle? What tool can be used? Anyone can help? How can we measure angle?
Sir, a protractor
Protector?
to measure
Yes, you can
angle.
use that to measure angle. So we want exact angle. So you need to use a tool to measure the angle, provided that the axis here is correct. Correct means they are at the same, what we call the same size, the same length, same scale, same scale. If they are in the same scale, then you can use protector directly. If not, you have to do some adjustment. So we find 62.87, and this is the point that we interested. This is the closed loop pole that will give overshoot 20%. Once we get this, the next question is, of course, we want to find K. How can we find K from here? We have 3 poles, one here, one here, one here, 3 poles. Then, as the formula that I mentioned to you, we get the length L1, L2, L3. So K is L1, L2, L3. That K, if we implement here, we get overshoot 20%. This is how we design a simple gain adjustment in order to get desired specification. In here, the desired specification is 20% overshoot. Any question? Now I want you to do at home as a homework. sketch this root locus. So you will get this, you have 0, minus 1, minus 4. Then you sketch the root locus, applying rule number 1 until rule number 8. If not applicable, then you skip the rules. Then apply rule number 9 to get K. Find K so that system operate at damping ratio 0.5. I want you to get K when damping ratio 0.5. Actually, the root locus is given here, but I want you to draw yourself before looking into this. And it will be good if you draw or sketch on a graph paper. Try to use graph paper. I would like to mention to you, we will not in the exam, in the final exam, in the test, we will not be asking you to draw or to sketch on a graph paper. We will not. We will give the root locus, and you have to interpret or read information from the root locus. But you will be perhaps you will be asking, you will be asked to draw or sketch a simple root locus, but not on a graph paper. But you have to know, of course, the basic theory on how to sketch. But for this example, I want you to sketch on a graph paper, so that you can increase your understanding. Why graph paper? Because later we want to find a point here. Without a point, if you just sketch on a plain paper, we could not get the coordinate. In order to us to get the length, L1, L2, and so on. That's why I want you to draw on a graph paper to get all the information. And use the right tool to measure damping ratio 0.5. Then calculate K. Okay. The answer is already given here. But try yourself first, then look into compare with the answer. This was obtained by using MATLAB. Later we discuss about MATLAB. Any question? We stop here. We will continue tomorrow with starting from here. I hope that you do this homework today or tonight before the class tomorrow. It is if you practice this, it will be good for your test and final exam. And your just to remind you, next week there will be a quiz on root locus. It will be on Thursday.